introduce you to cosmology. Do you have any lectures in cosmology already?
Yeah, one.
Okay. So I hope there's not too much of overlap with what I tell you. But what I will tell you is only one aspect of cosmology, which is kind of, in my opinion, driving the progress in cosmology in the last couple of decades. And that's more to do with the universe, not as just a homogeneous universe, but perturbations in it, the perturbed universe. Okay, so that would be the focus. So we'll get to that first with the introduction to what cosmology is all about, and as I go over the slides, the main thing that will determine how much you get out of the lecture is the questions you ask, or you can stop me. Okay? Otherwise, I'll just keep going on. So let me start with this, which I'm sure doesn't need to be done, but the realm of cosmology I'll be talking about is where a galaxy is basically like a tracer particle, right? You know, a galaxy is a pretty huge thing that you must have learned, so I don't want to tell you about all these numbers, but a galaxy itself has 100 billion stars. It's a huge object. A lot of scientists spend their entire life studying how a galaxy dynamically supports itself, what happens, a lot of procedures, lots of it's an interesting system itself. But for the cosmology that I'll talk about, okay, the galaxy is just like a dust particle that you're trying to understand the airflow in the room. Okay, it's just a tracer. Okay, so that's just to set the scale on which we are looking at astrophysical phenomena. Now let's look at the atlas of galaxies around us. Okay, this is sort of the local neighborhood in which we are. Okay, we are at the center here, and this cloud of particles that you see, okay, are basically each point is a galaxy. So these are actually clusters and superclusters, clusters and superclusters. Say here, for example, the Coma supercluster. There are various things, and this is how stuff looks around us. Just like you would make a model of solar system, this is the model of the local cosmos. Okay, and just to set the scale, here is a little stick which tells you how big is 100 million light years on this scale, right, of this plot. Now you can zoom out further. This is not really, as I said, this is local cosmology. At least the cosmology I'll talk about, we just say it's the local stuff. We don't really care about it. I zoom out by a factor of 5, then I really cannot plot superclusters as, you know, agglomerations. They become points themselves. Okay, this is the kind of distribution. Now if you were to put all the information that we have of the distribution of matter around us, okay, there are surveys which have surveyed galaxies. This is the picture you have. Now you see this stick here is 5 billion light years, right? And everything here, like every spot here, is a huge agglomeration of mass. And now what we can do is just cut out a piece of it. This is fairly a sample of the universe on cosmological scales, right? This is where we get to the realm in which I am talking about. And let me ask, okay, how does a typical neighborhood looks? So you take a box, hypothetical box, and cut it out, and zoom in and look at what the distribution looks like. This is from real data. Okay, this is actually from the 2-degree field survey, and this is a part of that survey, where each side is 100 megaparsec, right? About 300 million light years on the side. Okay, and what has been done here is, for every place the galaxy has been seen to exist, a toy image has been put, and the color reflects the color of the galaxy. That's unimportant for what I'm telling you. This milky stuff is not really real. It's just to help you see the amount of clustering that is there, right? So you can already see that the universe has galaxies, huge number of galaxies. They're spread out all over. But on the other hand, the distribution is pretty interesting. Okay, it's got this cellular distribution of mass in the universe. So it's definitely not a bland cosmos, right? And then the question is, this is how a typical thing looks like. And suppose we were to start cosmology now, with all the information, observations first and theory later, then you would really face a very tough question of how do we even hope to comprehend such an immensely large universe. Because every piece of it looks like a very complicated, thing out of a sponge or something like that. It's not simple. So the kind of perspective I'll give you is not historical. Historically, it didn't go like that. But suppose you are on physicist or associated with physics, so you might ask the question, now I have this problem. I want to understand the universe, and this is my observation. It's full of galaxies. Galaxies are distributed in very intricate patterns, and roughly every box of it looks like the box I showed you, right? So what do you do when you are faced with a problem in physics which looks very complicated?
Make it simple.
Pardon?
Solve it by pieces.
Solve it by pieces, that's one. And the other thing you do is you look for simplifying assumptions, right? You try to make the problem simple because all the Halliday and Resnick you've solved on frictionless slides and perfect things, you know that they don't really work in real life. If you really test out, you will find small differences because friction was neglected in your calculation. A ball which is rolling up a ramp, falling down and rolling up doesn't really get to the same height. Okay, so you'll have to take into account that. But on the other hand, there is some value to this simplicity, right? Because most of the things are captured. If you're really worried about that tiny difference, you would never know that energy is conserved, right? But roughly, energy is conserved, except for the fact that it's not an ideal system. So similarly, if I'm faced with this problem, I would look for an appropriate simple model. Now, where is the simplicity in this? Okay, and simplicity comes from this picture. So suppose I was not worrying about the three-dimensional distribution of galaxies, but just how they were placed in the sky around us. Right? That's typically how astronomy is done, right? You don't care where particular star is, like where the top Sirius is. You just look at the sky and you know what's the distribution of stars in. Okay. Similarly, I just project back all the galaxies onto the sky without worrying about how far they are. Okay? That means I am integrating over every solid angle and asking how much mass is there in every solid angle around me. Okay? Now if you look at it, this is a very old survey. So even in the 70s, observation it was very clear. The distribution of galaxies is not markedly different in any direction in the sky. Okay, if you're blessed with glasses, you take them off and you see it's basically there is clustering, but more or less it's not as if in the north there are a lot of galaxies, in the east there are not. Okay, so broadly, and this zone which you cannot see is the zone of obscuration because we live in a galaxy and there are parts of the sky which are not accessible to us optically. Okay, there are much better pictures now, but I just wanted to show you an old one from this leak survey because just to drive home the point that even 50 years back we roughly knew that the universe is isotropic around us. The distribution of galaxies, the matter distribution, did not have a preferred direction. It's not as if the universe had all galaxies in one direction and nothing in one direction. Okay. Now even with that, what you can do is, now you say, okay, the distribution of matter is isotropic around us. Then you take one step which is a leap of faith. Something like a super Copernican principle. You also assume that we are not in a special galaxy. It's not as if the universe is isotropic around us. But if I were to go very far away to another galaxy and did this map of galaxies around me, I would find that the universe is isotropic around that. Because there's no special role for us. Unless you are, and science has been moving like that for 500, 600 years. So if you do that, then immediately there's a little thing in maths you can use. So if you have a medium which is isotropic around every point, then that medium has to be homogeneous. Okay? And it only works one way. I invite you to think about it. If it's homogeneous, it doesn't mean it's isotropic. Okay? But if it is isotropic around every point, so this helps in anything, even if you're doing condensed matter physics. If the stuff is homogeneous at isotropic around every point, then that medium is homogeneous. So roughly, what this tells you already, that the universe, distribution of galaxies in the universe is homogeneous. Although we are sitting at one point, we have used this little mathematical thing to understand the universe on all scales, saying that anywhere you go, the universe is the same, right? Okay. But this is what you see in matter. But here you might argue that, okay, I see a lot of clustering. So why do we have a lot of confidence in? To what extent do we know it's isotropic around us? The biggest support for that comes from something called the cosmic microwave background. Okay, I don't know how many of you know it. Cosmic microwave background sits very close to radio astronomy. Okay, this detection was done by a radio horn in 1965. One of the radio horns built in Bell Labs was looking at the sky, and they found there was a 3 Kelvin excess noise that they couldn't explain at all. Okay, and it didn't change with the day, night, time of the year, where do you point. And a lot of people spend a lot of time trying to figure this out. And interestingly, what Govind Swarup told me is that he was in Stanford at that time, and people asked him to actually come and take a look as to what could be the possible problem, right? And he couldn't because of some personal commitments. So this is, as you all know, that Penzias and Wilson made this serendipitous discovery that there is an isotropic black body distribution of photons around us. You look at any direction in the sky, if you measure the energy spectrum of the photons, it corresponds to a temperature of 3 Kelvin, and that is 2.725 with this accuracy anywhere in the sky. You look any direction in the sky up to third decimal point, the temperature is the same. Okay, so isotropic black body, that is interesting. But then, if you really do your little bit of statistical physics, many of you may know Planck distribution. So a black body is a Planck distribution. For a Planck distribution, you actually, given the temperature, you can find the energy density. To find the energy density, you would find that the dominant radiation content of the universe is contained in this, very weak 3 Kelvin bath. It looks very cold, but that actually accounts for 99% of the radiation in the universe. So what does it tell you? That not only is the matter isotropic around us, the 99% of the radiation in the universe is distributed isotropically. And that is the extent to which we know that the universe is isotropic. And again, if you say that it's isotropic around every point, then you will get to this simple model of homogeneous and isotropic universes. Okay. Now what I forgot to tell you is, historically, actually this was put in as an assumption. So when Einstein built his first model of cosmology, he said, let's start with a homogeneous and isotropic distribution of matter. That was just because he wanted to solve the simplest problem in GI. Right? But now, observationally also, the microwave background puts it on a very strong footing, that this assumption that you've taken is absolutely valid to this extent. Right? Okay. So this is just to convince you that indeed this is the dominant contribution to the radiation in the universe. So you know that radio waves are very weak in terms of h nu, right? Frequencies are very low. CMB is just above the radio band, right? So here you are at 1 gigahertz. CMB the peak is at 70 gigahertz. So between 60 and say 600 gigahertz, the cosmic microwave background is dominant, and you can see that it's orders of magnitude above anything else. Okay, here's the gamma ray background, the X-ray background. The closest is far infrared background. These points are upper limits, right? So definitely you are kind of 99% dominated by the cosmic microwave background. And if you wonder why, again, if you know statistical physics, take a Planck distribution, ask how many photons you would have. You'll find that there are 400 photons per cubic centimeter for a 3 Kelvin bath. This sigma T4 kind of thing, right? That means everywhere now there are 400 CMB photons going through us. If you take a TV and yank off your cables, you see a phase. Okay, 1% of that is cosmic microwave background. It's that tiny percent because TV frequencies are lower than the cosmic microwave. If you had a TV working at 70 gigahertz, this is dominated by cosmic microwave. Okay, it's everywhere. Okay. Now, how do we know it's a black body? Initially, of course, with the first measurement, it was assumed to be black body. But in 1990, COBE satellite had an instrument called PIRUS, and it measured the energy at different frequencies in the microwave background. And it measured it between 60 and 600 gigahertz. Okay, and you can see these are the error bars with points with error bars and the line going through it. The line is a Planck spectrum, and you can easily, I think all of you will be convinced that this is an extremely good fit. But what is astonishing here is the error bars are actually 400 times magnified, so that you can measure them, you can plot them. Otherwise they are invisible. The error bars are 400 times smaller than what has been shown here. Okay, so this is one of the most accurate measurements made in astronomy to date. Okay, so when this was announced in the AA's meeting, the entire room stood up and clapped, because it's one of the amazing things. So what you now know is the cosmic microwave background is the most perfect black body spectrum known in nature. So one of the major challenges for experiments which try to measure cosmic microwave background differences, which I'll talk about later, is to actually have a calibrated load which is as good a black body as the microwave background. Okay, sometimes it's better to use the microwave against itself as a calibrator. It's so good a black body. Okay, but for the story of cosmology that I'm telling you, what's important is not only is the radiation distribution very isotropic around us, it's also very simple. I just give you the temperature, and that's all I have to tell you. The entire 99% of the universe is 99% of the radiation content of the universe is determined by one number, the temperature of the cosmic microwave background. Okay. Now, if I have a homogeneous universe, it's one of the simplest problems in general relativity. I didn't want to go into any of that, but all of you know in general relativity, the whole idea is curvature of space, time is equated to matter distribution. Now I am just solving the simplest problem in GR by putting a homogeneous matter distribution and asking what kind of space-time I get. And the biggest surprise was, and you may know this story, Einstein, when he did this, he found that none of his solutions were static. Okay, till that time everyone thought that the universe is kind of a very old, non-dynamical thing. Okay, but he found that there were no solutions which were not evolving in time. Okay, now that was initially he tried to cover it up, but soon Hubble found that it is indeed correct. So this is the picture I would like you to have. So it's not as if the universe is expanding around a particular center. Okay, the picture you should have is of a rubber membrane which is magically getting stretched. Okay, so you can't say there's no center to it. At any point the rubber membrane is stretching. So this is what is being shown in this animation. So these dots are basically coordinates on the space, and you can see that basically the physical distance between the points. So what was 1 centimeter at some time becomes 10 centimeter, 100 centimeter in this expanding universe. Okay, and then the expanding universe has interesting things which I just want to point out here. What is being shown is 2 points, say 2 galaxies from which there was a supernova burst and radiation is coming out. You can see that light, when it's traveling on a expanding membrane, which is like the space, actually has to fight the expansion. So you can see that the red things are actually slowing down, right? Seem to be slowing down. So you can have space-times where this expansion rate is so high that actually light can never catch up. So this galaxy might be emitting something which will never reach a galaxy sufficiently far away. Okay, such things are also possible. This is just as an aside. Okay. But this is the simplest way to understand what Hubble saw. What Hubble saw was, he measured the redshift of galaxies around us, and he found that every galaxy seemed to be moving away from us. And further a galaxy, faster was the recession speed. Now you could think of it like an explosion, but in an explosion you should remember, and I want to emphasize this because when you watch BBC serials on documentaries on cosmology, they start with this boom, boom, and it's like an explosion. It's not an explosion. First of all, contrary to an explosion, in an explosion the particles get slower as you go far away. Here, as you go far away, the particles are moving faster. So it's nothing to do with explosion, it's expansion. Okay? And so the velocity, so if the rubber membrane, two things are 1 centimeter apart, that becomes 10 centimeter. But the two guys who are 10 centimeter apart have become 100 centimeters. So they would apparently be moving much faster from each other. The second point is, it's not really a velocity. No particle is moving. In this thing, none of these points are actually moving. They are stuck to the same spatial location. It's space between them that is growing. Okay, so you should not think of it as a Doppler effect. Okay, locally you can, imagine it to be a Doppler effect, but it's not a Doppler effect. Okay, and I want to make these points. If you learn a course on cosmology, you will understand it better. Okay, in the context of the simple model we have, it's very, very interesting, because this expansion rate completely determines for you what is the typical characteristic density of the universe. Right? If you're working in any kind of physics, like if I'm doing gas physics or working with liquids or a neutron star, typical question as a physicist you will be asked is, so what's the typical energy scales or density scales you're working with? Right? So as a cosmologist, if I want to answer that, my expansion rate immediately translates to something which is known in literature as the critical density, but I'd love to call it a characteristic density. That's the characteristic density of the universe. If you ask me how much matter is there per unit volume in the universe, there's 10 to the minus 29 grams per cubic centimeter. If I took all the matter, smooth it out, this is the matter density. The other thing that comes with expansion is, these are, okay, now another thing I wanted to emphasize is cosmology, everything we do in cosmology is basic physics, but you have to just improve your intuition to doing it in an expanding space, right? A way to think about it, if you really wanted to spend time thinking about how cosmology works and didn't want to think of a rubber membrane, you just think of an ant walking on a elastic band which is expanding. And every effect that you see in cosmology, you can understand in that context. And I'm not joking, it's that simple. So every physics that we do are physical laws, but just as if you're doing it on a string which is expanding. So if I send a wave on it, for example, on a, if I had a string and I generate a wave, it would be a sinusoidal wave, right? You would set up something. But suppose the string was expanding, then what happens is while the wave is moving, the string has expanded. Okay, stretches the wavelength, and you would find, so something which was doing lower sa, higher sa would go to a lower sa soon. Okay? If you are doing acoustic physics, every physics is simple physics laws, but in an expanding universe. Okay, so you should not be scared by cosmology. The physics is exactly what you have learned. Okay? And the only thing you have to do is think about what happens if I am in an expanding box. So now let's do this thing to see how well you do it. So now I look at a box, like that box I cut out, 100 megaparsec box. There are say 10,000 galaxies there. Now the universe will expand, right? So how would the density of that box decrease? So number of galaxies will remain the same. The box goes up by a factor of 2, say. Then density will fall by a factor of 8. Good. But now imagine, I'm talking about the cosmic microwave background in that box. It's radiation. Okay. Now the box expands by a factor of 2. Number of photons decreases to by a factor of 8. But every photon, its wavelength has increased by a factor of 2. So what happens to energy density?
Decreases.
It catches another factor of 2, right? So it becomes 1 by 16. So with the size, matter density falls as 1 over volume, but radiation density falls off faster as the universe expands. Okay, the interesting thing about that is, although we have a 3 Kelvin bath now, and it is only contributing 1 part in 10,000 of the characteristic density that I talked about. When the universe was 10,000 times smaller and earlier than that, it was entirely dominated by this beautiful, smooth radiation dump. So the early universe is radiation dominated, and it's very simple. You don't care about all the matter. You could have all the quarks, all kinds of things, but it's essentially all for all practical purposes. Cosmic microwave background tells me what was the energy in the universe at early times. Okay, so you can see that how much we have got by just building a simple model, right? Okay. Now there is a little complication because of general relativity. In general relativity, of course, space is evolving in time. Okay. Now spatial hypersurfaces are homogeneous surfaces because the matter density is homogeneous. It is a space of constant curvature. Okay. Constant curvature, but then we are only used to mostly doing things in Euclidean geometry, right? All your geometry classes till now have been, or yeah, I guess most of you would have not have hit non-Euclidean geometry. Okay, so that's like living on a sheet paper, right? So what is characteristic about living on a sheet? Euclid's axioms work. So if I draw a triangle, the angles add up to 180. Now, if you know the history, you know that every mathematician of any caliber always questioned Euclid's axiom because there was one which was very obnoxious. The fact that two parallel lines remain, never touch each other, right? But on a sphere, two parallel lines do cut each other. I can be on the equator and both start north, we'll go and collide at the north pole, right? That's the difference between Euclidean and non-Euclidean geometry. And if I draw a triangle on the surface of a sphere, the angles add up to more than 180. So that is a universe with constant positive curvature. Okay, and you just have to imagine that in 3 dimensions, but that's okay. 2-dimensional intuition is fine. So I can have 3 kinds of universes, and that's very, very simple. I have constant curvature, and a constant can be either 0, positive or negative, right? So there's no big deal about it. So we already know that the universe can come in one of the 3 types. Okay. Again, because we had this simple model, there is a very nice way of knowing whether the universe is positively curved, negatively curved, or a consequence of that. If the universe is positively curved, then the energy density of the universe is greater than the characteristic density. If it's negatively curved, it's less than the characteristic density. And if it's exactly flat, then the energy density of the universe is the characteristic density. Okay, and how would I observationally know that? I have to draw triangles on billions of light years size. Now that sounds funny, right? How do you draw triangles and measure the angles? But that's exactly what we have done. So that's what this story I'll tell you. So essentially, if you do a course on cosmology, you would know that all that is there to the basic model of cosmology is there's this universe which is expanding in time, and I have to tell you how the expansion evolved in time. Right? So here's the universe which expanded and recollapsed. Here's the universe which is expanding forever. Here's the universe which is expanding forever, but then the expansion rate becomes constant. Here's the universe where the expansion rate keeps increasing. Here the expansion rate decreases with time. Here it's constant. Here it's... So you can have all kinds of things. But the interesting part, again because we have a simple model, is all I need to know is the expansion rate now and the current amount of matter that clusters under gravity. Okay, and this is something you're familiar with. Any matter clusters under gravity. But unfortunately in cosmology, we also have to contend with the fact that there can be matter which does not cluster under gravity. It has pressure which is negative and which keeps it from clustering. If I know the relative amounts of that, then I can exactly tell you what the universe did in the past and will do in the future. Okay, it's interesting. Simple model, but I can make very profound conclusions about our origins and our destiny. Okay, let me ignore this, but let me not completely ignore it. I just wanted to again drive home the fact that cosmology, the model is so simple that all of cosmology, after you learn it, then you realize that it's just an algebraic equation. You take all the energy densities divided by the characteristic density, and we call them omegas. So it's rho m by rho critical, that is called omega m. This is vacuum density, this is curvature density, radiation density. They have to add up to 1. So after a month of course, you would be a bit disappointed to know that all you have learned is an algebraic equation. Okay, but that's what it is. But that makes it easy to figure out what will happen. So in particular, at this point we know that radiation density is small. So there are 3 major players. How much of matter that clusters, how much of matter that does not cluster, and the curvature. Okay? So if I know these three things and the expansion rate, because I need to know the expansion rate to get the characteristic density, then I know basically everything that I need to know about the background cosmological model. Okay. Now the question is, how much do we know about this model universe? Okay. So when I started my research, that was like 1990 when Kobe was launched at the same time. That time things were not known too well. Cosmology was in the realm of, a lot of physicists would laugh at cosmology and say, okay, but look, you might have heard of Landau's famous comments that cosmologists are never correct but never in doubt but never correct, or something like that. I forget the exact wording. But what I wanted to tell you, at least in my own career, it has evolved to that, and we really know lots about cosmology now. So how well do we know? So it's a good old cosmological model, but what is the new trend? We know that the total density of the universe is exactly the characteristic density, and this accuracy is less than a percent level. These are old numbers, okay? To a fraction of a percent, we know that the universe is exactly flat, geometrically flat, evolving in time. That's amazing, right? Sitting in a small planet, being able to tell you that. We know that there must be energy in vacuum, in the sense that there is matter in the universe. 75% of the density of the universe is made up of stuff that is like vacuum energy. Okay, this is a revelation. It's a challenge to understand where it comes from, but we know it for sure. We know that matter that clusters forms the complement 27, and matter that we are made up of, all the matter particles that are known to us now, only constitute 4% of the energy density of the universe. Okay? And then of course we know the expansion rate very well, and this is again old numbers, it's improved much better than now. So we know that the Hubble constant, which tells you what is the expansion rate between two galaxies separated by a megaparsec. It is 71 kilometers per second. So if I have two galaxies 100 megaparsecs away, they are moving away from each other at 7,000 kilometers per second. Okay? If they are 1,000 megaparsecs away, that much, proportionally be relative. Okay, good. And we also know the age of the universe very well, which is amazing. We know that the universe, as we think, it started from some kind of a very dense state. That has lasted only 14 billion years. The universe is 14 billion years. Okay, 13.7 if you want to be careful. Okay, so the whole job in the rest of the talk would be to tell you how we know so much about it. Right? So how we know about all this is because earlier we were only worried about understanding the background evolution of the universe. But then we started asking, okay, but if I look at a typical box, there's all this intricate structure of, called large-scale structure, intricate distribution of galaxies. Now where did that come from? When we tried to understand the part of the universe, that's when we started learning more about the background universe. So let me go to that, but before that let me tell you what is the tool we will use in doing that. It's the cosmological background, so let me tell you a little more about it. So the universe is like a sheet evolving in time. So I can't draw 3 plus 1 dimensions, so I'm drawing 2 spatial dimensions evolving in time. Right? So this is, we are here and now. If I want to go and look in the past, all of you know that speed of light is finite. So I can only look within this light cone. And in particular, cosmic microwave background photons are traveling to us on the surface of this cone. Right? So as I look out from here, when I see a galaxy, I always see it as it was in the past. Right? When I see the sun, you may realize that the sun is 8 minutes already. So if there's a hiccup on the sun, we are seeing it only 8 minutes later. Okay? If the sun goes boom, it will take 8 minutes for us to know. Okay? But then when you look at a faraway galaxy, that 8 minutes become billions of years. And you can ask, okay, how far can I look back peer back in the electromagnetic observations? If you really, there's only a window in that, and that's between this, I told you, 60 to 150, 200 gigahertz. where there's nothing which obscures things, and you can look way back to this surface, which is 43 billion light years away. Okay, so you can look back into your past when the universe was 1100 times smaller. Okay, so let me show you a picture which is slightly different. And okay, the other thing is, as I'm going back in the past, you also realize the universe was smaller in size, densities were higher, and in fact radiation was hotter. And since radiation density is sigma T4 and density falls off as 1 over L4, so temperature is just proportional to size. So if the universe is 1100 times smaller, the temperature of the microwave there was 3000 Kelvin, 3300 Kelvin. Okay. Now this is sort of a space-time diagram, but as far as observations go, or the best way to understand, look at, imagine it, is we are in a very unique situation. We are sitting here in this tiny planet looking out. I can actually look back 43 billion light years, okay, to this surface from which this microwave background is coming. Okay, why is it coming from this surface? Because before that, the universe, temperature of the universe was higher than 3300 Kelvin. Now, most of the universe is made up of hydrogen and helium, right? 70% hydrogen, 75% hydrogen, 25% helium. You take such a gas and heat it to 3000 Kelvin. Okay, even lab physics, you would know that it will turn into a plasma. Okay, so the universe was essentially plasma. Electrons never stayed close to a proton, they were just free charges going around. Now what happens in a plasma? Plasma means if the electron is free, then it scatters of light very effectively. Okay, so these were really absorbing and emitting the radiation. So if you really dump a lot of radiation into a plasma, it very quickly gets thermalized. So the universe before this is where all the radiation that happened, all kinds of physics could have happened before that, and that sort of all totals out to give you that thermal distribution. Yes.
So I have a very basic doubt actually. I mean, here are we looking 43 billion light years away?
Yes, onto the surface.
Which means that it is 43 billion years old, right?
Yes. No, it doesn't mean that, because the universe is expanding. So it's light years and this thing. This is a good question you asked. So this is basically because of the expansion. Okay, so since you asked this, so imagine an ant walking on a thing, right? You ask how much distance did it cover, right? So you would think that as it is struggling against the expansion, it's covering less and less. But imagine the 1 centimeter it had covered. Okay, suppose it covers 1 centimeter in the first minute, then it covers another centimeter, and by that time this whole thing is stretched to 20 centimeters. Okay, so although the ant has actually walked 2 centimeters, it would have travelled 20 centimeters.
That means like,
so that's why the light, although the light is struggling with the expansion, but the little distance it covered becomes very large now. Right? So when I'm saying 43 billion light years, so all distances, so this is a good point. So when we talk about distances, you can always ask at what time. So we always talk about the distances in units now. This 43 billion light years, 1100 at the time when the universe was 1100 times smaller, so 1100 times small in physically. Okay, so think a bit more about this ant walking. So you can see that although it covers 1 centimeter, since that 1 centimeter has become 10 centimeter, it appears to have travelled a lot more. Similarly, the light although it's travelling for only
15 billion
about
years.
15 billion years,
But space has expanded.
Space has expanded, so it is actually corresponding to 43 billion light years. This translation between 14 to 43 depends on what is the cosmological model, how the evolution happened, and it's a simple integral to do and figure that out. But that's about that. I hope that answers your question, right? Okay, but I'm glad you caught that. Okay, now what is the physical picture? Yes.
So if this radius is 43 billion light years, it means that that's more than what light would cover in 14 billion years.
Yeah.
Exactly.
So isn't it like initially it was the speed is more than the speed of light?
No.
Speed of expansion.
It's light always travels at the same speed, right? That's special relativity.
Yeah.
So the point is the ant keeps traveling at the same speed, 1 centimeter per minute.
Let's suppose that there are
Okay.
two ants walking on opposite ends. So
Yeah.
they will
may never get to meet each other because their space has expanded.
yeah. So they will just I'm saying they're going away from each other. So they will just keep on going farther and farther.
Yeah, but
the distance between them is also increasing at
Yeah.
a very high rate.
yeah.
But because of that, since the distance is increasing in such a way that here in 14 billion years, this whole universe has expanded. So, and it's expanded to more than 14 billion light years. So it means that it's expanded to more than what light could travel in this much amount of time.
Right. So that's what I'm trying to tell you. That if suppose don't worry about two ants. Suppose ant starts from the go mark and travels 1 centimeter per minute. Okay, so it traveled 1 centimeter and then it traveled another centimeter. Okay, but this 1 centimeter traveled, suppose it's becoming 10 times larger every minute. It becomes 10 centimeter. So the ant, although it has actually physically walked only 2 centimeters, the actual distance it has covered is 20 centimeters. So the amount of time, so then you would infer that the ant is moving at 20 centimeters, 10 centimeters per minute. Isn't it? Okay, let's do this. See, there's this string which is expanding. Here's this ant. Okay, it moves at 1 centimeter per, okay, velocity is 1 centimeter per minute. And the ant is like light, it doesn't change its velocity, speed. So it sees this medium in front of it and walks at that speed. Okay, now after 1 minute, the ant is, suppose I mark it with a blue mark pen. So this mark actually sits at 10 centimeters, right? So if once it has come here, the ant actually has not walked 10 centimeters, but the space it has covered, distance it has covered, corresponds to 10 centimeters now. It will correspond to close to 1 centimeter then, but it corresponds to 10 centimeter now. Next step it would go another little bit here, but then this has become 100 centimeters, right? So this, I'm not saying it's easy to understand, but this is the model. So if you think about it and if you have doubts, please come and ask me, but everything in cosmology you can understand like this.
Does it again?
Yeah.
So is that implies that the rate at which that space is expanding is more than the speed of that ant?
It's not necessary.
No, but it might be, no?
It could be. That's what I told you. Then the ant would never seem to be moving much. That happens.
So now the rate by which the universe is expanding is more than the speed of light?
At this point, interestingly enough, it is. Okay, it's not, I mean the rate at which, but the point is, we are in a, currently, if it is dominated by that dark energy that I told you, or vacuum energy, then we are in a universe where slowly what would happen is, galaxies we could see now will drop out of sight, very far away. Okay? So slowly, we won't see anything other than things which are very close by. At the end of it, it's a very bleak destiny, so I don't want to even talk
And
about it.
also, like when we are talking about a space expanding from that point of time, like from the start, did the laws of physics that we know of did apply at that time?
Yeah, so okay, now that's a good question. So I don't know whether I have these plots, but okay.
See, our laws of physics are based on 4 fundamental forces that are active.
They were not existent.
Yeah, so we believe, okay, so as I said, we believe that we can use the laws of physics. So let's see. So at some point, this blue thing would be very close here, right? Because it's expanding all the time, the string. So when I started from a stage where this was 1 centimeter, but at some point it was a micron away. Then it was a nanometer away. Right? This blue mark would be like that because the universe. But the question is, where do you stop this? Because if I extrapolate it to some point, it would seem all the blue marks that I put at this equal distances will all come together. Right? The volume of space will become 0. Right? Because, but you should realize that that's an extrapolation. We have no business doing that as such. It's a mathematical model, which it is something like you see of expanding. Suppose you see a vent from which air is expanding. Now I took the particles and marked their trajectories. Okay, I went back in time. Okay, and then I can only go back so much. And then some mathematician comes and says, okay, now your model, if I take the straight lines together, all the matter was in one point. Yeah. That looks funny, right? So that is not necessary. That's mathematical model stretched to the limit. But yes, I mean, we use that as a convenient starting point, because if you extrapolate that, it comes to that point 0. It's a reference point. But what is interesting is, now you can ask, how far can I go back with basic physics? Okay. Now I said we are at a time when we are 14 into 10 to the power 9 years, right? We can go back and use laws of physics which are well tested in lab when the universe was 10 to the minus 16 seconds old. Okay? If I really think LHC is detecting, doing the right physics, and we have understood the physics at the LHC, then that goes another few orders of magnitude back, right? 10 to the minus 20 or some seconds. Now my feeling is, if I have understood the universe from when it was 10 to the minus 20 seconds old to when it is 14 billion years old, I think we have done a good job. Okay, so the last part, yes, it may be very interesting, but it's not as if there's a major problem with cosmology. Okay, we know that we have to understand higher energy physics to understand that, and there are models. Now the question is, how do we test them? Okay, and the interesting part is, beyond LHC, we cannot build any more accelerators bigger than that. The highest energy particles we see are in the cosmic rays. Okay, they are about 10 to the power how much? 10 to the power 9 GeV or something like that. But the physics we are looking for is 10 to the power 16 GeV. Okay, giga electron volts. Or Planck scale, which is 10 to the power 19 GeV. That's where we don't even have theories. But the question is, as far as I am concerned, personally, I am happy that we understand with our basic physics that we know the universe as it was about 10 to the minus, say 20 seconds old, to up to now. There we have no doubt. We just use the basic physics that we use, all particle cross sections, everything, all this thing uses just basic physics. That is lab tested. Okay.
Sir, the size of the visible universe up to which what we can see, it's basically 14 billion light years.
43 billion light years.
So we can see
look up to. So that's what I said. Up to in electromagnetic, with electromagnetic probe, we can look up to this entire place because the universe is transparent here. Then we hit essentially a fog wall. Right, because beyond that what happens is, even if there's something interesting happening, I cannot see it because it's a plasma. So it's just kind of, the light scatters so much that I don't have, just like you can't look in the fog, because if suppose a fog descended now, right, I may be able to see his face, but I may not be able to see the backbench. Right, what is happening there? It's not as if she is not sending out any light signals. The light signals come through the fog and get so mixed up that there's no coherent picture I can make. That's the situation with electromagnetism thing. This hitting this fog wall means beyond that I cannot have any coherent information.
So but the light that we can gather should only be about 14 billion light years away, not more than that.
Why? This is up to 14 billion light years old. Yeah, the light cannot be 14 billion light, but it could have traveled 43 billion light years because of the expansion.
If it would have had traveled 14 billion light years, then it would have been 14 billion years old.
No. So the point is the distance that you're traveling, the space. Suppose I cover 1 centimeter, as I told you this, right? So if I cover 1 centimeter per minute.
I'm saying that if it covers 14 billion light years, then it has to be.
So light year is just a convenient unit of saying how far light would travel in 1 year.
Yeah.
Okay, that's a length scale. But that is in a situation where you don't worry about the space expanding in between. What I'm telling you is, if the space is expanding in between, then in 1 year you might be traveling for 1 year, but because the space has expanded, the distance you've covered is much more than 1 light year. See, when you do light years Light year is just a conversion because
It's like light left and the galaxy is still receding back, so it will appear that the galaxy
it's not
is still
receding.
further.
Yeah, so galaxy exactly. So the point is light left, and you traveled only for a year. But okay, so maybe this will excite you more. How many of you know of this warp drive? How many of you are Star Trekkies?
Sorry?
Star Trek? Star Trek? You don't know Star Trek? Serial?
I don't watch.
Spock.
Yes, Spock. And all this thing. Okay. So you know that they have this warp drive?
Yes.
Okay? It is not something that people have not thought about. So if you want to travel faster than speed of light, what do? Okay? You eat up the space in front of you and expand the space behind you. Suppose we were magicians who could play with space, right? And I want to walk from here to meet him. What I do is of course if I wanted to walk, I will be slower than speed of light. Even if I wanted to send this pointer light, it will be slower. But what if I had a machine which, when I press this thing, not only sends out the light beam but also eats up space in front of it and expands behind, right? Then I would be moving faster than speed of light, right? So when you are in a situation where the floor on which you're walking is dynamical, things happen. What I'm trying to tell you is they sound very mysterious, but if you really think, okay, I'm not in a very I'm in a different situation than what I'm really used to in day-to-day life, then you can figure these out. And a very simple example of that is to think of an ant moving on a elastic band, right? So if ant wanted to move fast and it had an ability to eat up, instead of expanding the thing, forget the expanding, there's an elastic band and the ant is so great that it can eat up the elastic as it's walking, then of course it will eat up space. It will travel much faster than the speed at which it could walk, right? That he wants to get to that blue thing. Instead of really walking, it just eats up the space in front of it. That's warp drive. Unfortunately, conceptually, there's nothing wrong with it, but we don't know how to make it happen. Okay, but if we did make it happen, you can move. In fact, there's nothing technologically impossible about moving faster than the speed of light. If we not technologically, conceptually, nothing wrong. Technologically, obviously, challenge. Okay, so this is how the universe is here and now. Now, if I were to only look at the cosmic microwave background as a thing which is at the same temperature everywhere, then it would be just a blank screen. I'm looking out 43 billion light years and I'm seeing a screen of photons which are at the same temperature. Nothing interesting, right? So no one wants to sit in a IMAX theater with nothing being shown on the screen. I don't know how many of you pay for that, right? But what is interesting is what happened in 1992 is we started seeing tiny variations in the temperature of the microwave background. We saw that the microwave background, although it was largely uniform, but at 10 parts per million, the temperature did vary. And we expected that because we see that matter is nearly isotropic around us, but we do see it's clustered. And if matter and radiation were tightly coupled in the early universe, then it's just impossible for the radiation not to carry an imprint of that. It can be very subtle, okay, and it was really subtle. So this is the picture we have. So this is the screen cut, and if I wanted to paint it and look from outside, this is the fluctuations measured by a satellite. This is the current kind of understanding of how the temperature at different points of the sky in the microwave are different. Okay, so these are, as I said, tiny variations at 10 parts per million. So on a 3 Kelvin background, the temperature fluctuations are of the level of tens of microkelvin. Okay, so it is a big technological advance. Okay, let me skip this. And because of that, of course, Kobe got this Nobel Prize in '92. Now this is the information that you have on the sky. This is the entire sky, but plotted onto an oval. This is just a mapping. Okay, and you can see that certain parts of the sky are slightly hotter in the microwave and slightly colder in the microwave. Okay, so the background temperature is 3 Kelvin, and the variations here are between, the bluest spot is minus 200 microkelvins colder, and this is 200 microkelvins hotter. The RMS is about 70 microkelvin. Okay, forget all the others. Okay. Now what we do is we have now let's go back to 2 plus 1 dimension. So we had a uniform distribution on the sky, but now we are saying there is tiny differences, right? So what you have, if you have a function on a circle, you expand it in Fourier series, right? I have a function on a sphere, I expand it in what I call spherical harmonics. If you have a hydrogen atom, you would know about spherical harmonics. And it's a random fluctuation. So there are coefficients which are random, and I can ask how much power is there in each coefficient. And that tells you basically how much power is there at different angular scales. I mean, is it that the temperature fluctuations are on very small angular scales or very large angular scales? And I can separate them out and tell you how much there is in everything. So let me give you an analogy. Suppose I have this desk. So normally if someone asks you how rough is the finish, you will give me one number, which is the RMS. And that is fine because it's everywhere the same, right, on all scales. But suppose I leave it in the rain, it will warp. So then you see that on very small scale, the RMS remains the same. But on large scales, it could be going up and down in centimeters. So then it helps to give you something called a power spectrum, which tells me what are the jumps in heights on scales when I'm measuring it at few centimeters scale versus when I'm measuring it at very small scales. So it gives you a lot more information than its RMS at different sizes. Okay, that is something called CL. Let me only point out that for the simple cosmological model, the CLs have to have some shape like this. Okay, and I'll tell you why. This is interesting physics, and depending on how the universe, what kind of universe you have, the shape does vary. Like if the universe is got characteristic density, then it would be this green curve. If it is more than the characteristic density, then it will be this red curve. If it's less than characteristic, it will be the blue curve. That stands to reason, if I measure the fluctuations well, I will get one of these curves, which rules out the universe being the other two. Right? Okay. So that's the game we have been playing. And this physics is very well understood. So that's what I wanted to emphasize. So although we are making profound statements using these observations, the physics we are used to infer them is very basic physics. And it's a physics of something that you have done in your lab, resonance tube experiment. Okay, so what happens there is you go back to this screen. I told you it's a plasma screen. Now what's interesting about a plasma is if I perturb the plasma, it oscillates. Okay, because matter wants to condense, but radiation pushes it out. So if the universe had perturbations, then this plasma screen is more like this. It's kind of going up and down, right? So there's some. It's not a very smooth thing, but this up and down is a very small amplitude, 10 to the minus 6. Okay. Now what can you say about it? Okay. So let's. Okay, this is, I'll get to this picture. So now if I wanted to study something, what do? You essentially throw a stone and try to, suppose I wanted to study waves on a surface of water. Then I'll throw a stone and look at the ripples going out. I'll measure how fast a ripple travels, right? That tells me how fast fluctuations travel on that. Okay. So similarly, when I want to analyze what happens when the universe is not completely smooth but has perturbations, I analyze what is called the Green's function, but what I will do is I'll throw a stone and ask what is the response to it. Okay. Now, just let's go back to an analogy. So suppose you're standing by the side of a very placid lake, okay, and there's a burst of shower. Okay, just once. Everywhere there are raindrops. Now everywhere a raindrop falls, there will be a ripple going out. Okay? And suppose I take a photograph after and the ripple goes out as 1 centimeter per second. I take a photograph 10 seconds after the shower happened. Right? What you would actually get on your photograph is completely choppy waters. Right? It looks like no information, just like the cosmic microwave background, random fluctuations. But if I was smart, okay, and I knew the physics behind it, what I can do is I can go to Fourier space and I would actually see that there around every place there's a drop. There is a ring around it which is traveled 10 centimeters. Right? So if you Fourier transform it, I have excess power at 10 centimeters. Right? So it's the same story here. If I took this plasma screen and only hit it once rather than worry about all the fluctuations, then what happens is there's a wave which moves out, okay, and it travels a particular distance, and then